We'll begin our basic work and energy ones here with this situation where we have a speeding bullet that has a kinetic energy of k. Another object has twice the mass and is traveling 2.2 times faster, and we want to know its kinetic energy. So this is a great one where we want to set up our original situation and our new situation. So for our original, we're just going to think about kinetic energy, which is 1/2 mv squared. For our new situation here, we're going to think about our new kinetic energy, so I'll call that K prime because it's not the same. And two things change. Our mass is now 2m because we have twice as much mass, and our velocity is 2.2 v, and that entire quantity is squared. Okay, so we go ahead and do our math here. We have K prime is equal to 1/2 times 2m times 4.84 v squared. What I'm going to do is I'm going to pull out these two extra numbers here. Okay, the 1/2 was part of our original equation, but I'm going to pull out those two extra numbers, the 2 and the 4.84, and multiply them together. And so I get that K prime is 9.68 times 1/2 mv squared, which was our original kinetic energy, which means that my new kinetic energy is 9.68 K. For this next problem, we have a situation once again where we're going to need to set up our new and our original. So we have a compressed spring with 8 joules of potential energy. When it's compressed a distance of x, it's compressed some additional distance and it now has 12 joules of energy. How far is it compressed? So I'm going to start with my original once again. I know that spring potential energy is given by 1/2 kx squared. So I can say that 8 equals 1/2 kx squared. For our new situation, I'm going to start with the same equation, 1/2 kx squared. Now my spring potential energy is going to be 12. It's the same spring, so my spring constant stays the same, but I'm going to say my new distance now is x prime squared. There are a few ways to solve for this. I can solve both sides for k. I can divide the equations. I have a few options. What I'm going to do is I'm going to divide the equations. So I'm going to take this original equation here and divide the new equation by that original. And so what ends up happening is my 1/2s cancel out, my k's cancel out, and what I'm left with is 1.5 is equal to x prime squared over x squared. I'm going to go ahead and solve for x prime, so I can say 1.5 x squared equals x prime squared. I take the square root of both sides, and I end up getting that 1.22x is equal to x prime. Up next, we have a purely conceptual one. So we have a situation here where a hand pushes a box up a ramp at a constant speed. The box travels a distance of x up the ramp. And our first question is, during this time, does the hand do positive, negative, or zero work on the box? Okay, and the answer here would be that the hand by itself does a positive amount of work on the box. Okay, we're exerting a force in that direction. Our displacement is also in that direction. So because our force and our displacement are in the same direction, that's going to increase the energy of the box, therefore doing positive work. Moving on to B, during this time, does the total energy of the box increase, decrease, or remain the same? And if we peek ahead to part C, we're asked then about the box-Earth system. So this is one of those ones where we're getting at the fact that potential energy is an energy that's stored between the box and the Earth, whereas the box itself only has kinetic. We know that the box is pushed up at a constant speed, which means that the kinetic energy of the box is going to remain the same, and that's the only kind of energy that the box by itself has. Okay, so the total energy will remain the same because the box is pushed up the ramp at a constant speed, and therefore the kinetic energy of the box, which is the only energy it has, does not change. The last one we're concerned about is the total energy of the box-Earth system. Does that increase, decrease, or remain the same? So we know the kinetic energy of the box remains the same. However, we do gain height, so that means that we are going to gain gravitational potential energy, and therefore the energy of the Earth box system will increase. That gain in height simply results from that pushing force from the hand, the work done by the hand, leads to an increase in the gravitational potential energy of the Earth box system, while the kinetic energy of the box remains the same. Moving on to this one, we have a situation where there's a force applied to 4 different boxes, pushing it over some distance, and we want to rank the work done in each situation. So what I would think about here is we're thinking about our idea that work is F delta X cosine theta. Okay, that's how we get the work done by a force, and we're going to think about some of the concepts that we know related to that. The first thing that I would see that jumps out to me here is box B. What I notice for box B is that the angle between the force and the displacement is equal to 90 degrees. And when the angle is 90 degrees, when the force is perpendicular to the displacement, the work done is 0. So box B must be the smallest one. Up next, we look at A, C, and D. They're all traveling the same distance, D. Okay, so we really just need to look at the forces. I see that object D has a force of 2F, so that has to be the most, so I'll ignore that for now. And then I'm just going to compare A and C. Looking at those two, I know for A, my angle is 0 degrees, and for C, it's something bigger than 0 degrees. And so that means that A is going to be more work done because we maximize cosine when our angle is 0. Right? When our angle is 0, cosine's 1. So C must be less than A, and then D is the biggest of them all. For this next one, we have an object with a mass of m that is attached to a string, and it's spun around in a circle on a horizontal table that is frictionless. And the radius of that circle is r, and we're traveling at some constant speed here around the circle of v. So the first question is, we want to know how much work is done by the force of tension in one rotation. So once again, I'm thinking about F delta X cosine of theta. And this might be a little bit confusing to think about because we're saying, well, the force of tension, which is going to be going inwards, providing that centripetal acceleration, that's always changing, as is the direction of my displacement. However, what ends up happening is the angle between my displacement, which is the direction of my velocity, and my force, no matter where I am, is always going to be 90 degrees. And so that means that the work done, no matter what, will always be 0 because my angle is 90 degrees. Moving on to question B, we want to know about the change in the kinetic energy of the object as it goes around one rotation. And what we know is that the velocity is constant here. So that means that there's 0 change or no change in the kinetic energy because its velocity is not changing. For part C, we want to know if the answers to A and B make sense, knowing what we know about work and energy, and the answer is yes. Work is the change in energy, so if no work is being done, it makes sense that there is no change in energy of the object. Moving on to this next one, we have an object sliding across a level floor, and we have a graph here showing the force. The net force is a function of the distance or of its position as it slides across the floor. First thing we want to do is find the work done over the entire distance, and so what we're looking for is the area. So I have 2 areas here. There's area 1 and there is area 2. And I'm going to calculate each one of them and add them to get the net work done. So for area 1, it's a rectangle, so base times height. The base is going to be 2x and my height is going to be 2f, so that means the net work done during that period of time is 4fx. For the second one, it's a triangle. Area once again is 1/2 base times height, and so my base there is from 3x to 5x, so 2x. My height is negative 2f, which means that the work done there is going to be negative 2fx. To get my total work being done here, I'm just going to add those two, and I get a total work done of 2fx, just adding the works done in each portion of the graph. For B, the question is, after traveling a distance of 5x, does the velocity of the object increase, decrease, or remain the same? We have a positive amount of work being done, which means the velocity of the object is going to increase. We know it's just sliding across a level floor, so that work being done is going to go into the kinetic energy of the object. C asks when the object is traveling the fastest, and so if we look back at our graph, we notice that from 0 to 2x, we have a positive amount of work being done. From 2x to 3x, our work being done is 0 because there is no force. And then for that last part, we have a negative amount of work being done. That means that this portion right in here is going to be when we're traveling the fastest, because from 0 to 2x, we are increasing our kinetic energy. Then it remains constant from 2x to 3x before it starts to decrease. So from 2x to 3x, we will be traveling the fastest because up until 2x, we had a positive amount of work being done, and after 3x, the work being done is negative. Alright, for this next one, we have a pitcher exerting force on a baseball with a mass of m in order to accelerate it from rest to a speed of v over some distance x. And we have a graph here of the force exerted on the baseball by the pitcher as a function of position. Okay, so the first thing we want to do is determine what is the kinetic energy of the ball when it is thrown. That is simply going to be 1/2 mv squared. We're given the mass, we're given the velocity, so there is our answer there. For the second one, what is the maximum force exerted by the pitcher? There's two things that we're thinking about. Number one, we're thinking about the fact that work is the change in energy. In this case, the kinetic energy of the object is changing, so we can say that change in energy is going to be K final minus K initial. Our initial was 0 because we started from rest here, so our work done on the baseball by the pitcher is just going to be 1/2 mv squared, that final kinetic energy. We also know that the work done equals the area under the curve here on this graph. So if we find the area of that triangle, which is going to be 1/2 base times height, that is also going to be equal to the work. So we can say our work done is 1/2. Our base here is x, our height is this F max that we're ultimately solving for, and so that's going to be our work done. We can take these two and set them equal to each other, and that's going to allow us to solve for that maximum force. So we can say 1/2 mv squared equals 1/2 x times our maximum force. Our 1/2s will go away, dividing them out on both sides, and we find that our maximum force then is just going to be equal to mv squared over x.